So we've had an introduction to UV spectroscopy and we've seen how that instrument works. And now I want to talk to you about how your Fourier transform infrared spectrometer works. It works very differently. It doesn't select a wavelength of light, shine that on a detector, and measure the power of that particular segment of light, and therefore determine which wavelengths of light are making it through the spectrum. It actually looks at all the light simultaneously using a broadband light detector that detects all the wavelengths and just tells you how much light's hitting the detector. It doesn't tell you which wavelengths. All it's saying is what is the power of light hitting the detector. But we can change that power by creating interferences within the light by using an interferometer. And these interference patterns are going to tell us about every single wavelength that exists simultaneously in that light. It's a bit like listening to music. If I wanted to listen to a symphony, I could use a special machine to sort out the sounds and just tell me when middle C plays. And I would sit there and I would listen to the entire symphony and I'd hear middle C whenever it played. And then I could go to D and D sharp and look at every note individually. Or I could listen to the whole symphony. And you know, some people, when they listen to a chord played by a whole symphony, can tell you every note that's in that chord. There are people out there that can transcribe an entire symphony just by listening to it. These are the people that have a Fourier transform infrared spectrometer in their brain for music. They can determine every single frequency by listening to the totality of the information. How can we do this with your instrument? Well, first let me introduce you to an important man, Albert Michelson. He was the first American to win a Nobel Prize. I believe he was the first physicist to win a Nobel Prize. He was a very, very important man. And there's a great quote here from a short story or an article written by Norman Maclean, who was a great American writer. And I think it captures the spirit of what Michelson did quite nicely. If you want to know more about the importance of Michelson, I encourage you to read up on the Michelson-Morley experiment. You'll recall that experiment from your high school and your university, your first year university physics class. It is one of the seminal experiments of physics and really of the world. It established an important aspect of the nature of the universe and really allowed the idea of the constant speed of light to be proven, which was really the core of Einstein's theory of relativity. So this is the man that laid the foundation for the house that Einstein built, him and Edward Morley. Edward Morley was a chemist, and Edward Morley was a man obsessed with significant figures. His perhaps most important contribution to chemistry was determining the mass of the oxygen atom to a great degree of precision. And so when Michelson was developing his diffractometer, his interferometer, his first attempt was to create a device in Germany, and despite having access to all of German craftsmanship, he was not able to create a device that was stable enough to give him results that were good enough to prove the point he was trying to make, that the speed of light would be different in two directions because of the fact that it traveled through a mysterious fluid called the ether. He was actually trying to prove that. Everyone thinks, oh, his experiment disproved it, but in fact he was trying to prove, or at least measure it. I mean, he just assumed it exists. I mean, come on, light cannot travel through a vacuum. What's that? That's nuts, right? So he was trying to measure this obvious fact that there must be an ether out there which light travels through. But it's a small effect, very small, and this instrument which he created wasn't able to show the effect of the ether. So he didn't interpret this as meaning there was no ether around, he just interpreted this as meaning I can't measure it. And therefore he proposed that the effect of the ether was much smaller than what people thought it should be, which of course is tantamount to saying that maybe it's not there. A lot of people criticize this experiment because there's just too much vibration. Look at those big long arms, they're 10 feet long, they stick way out. There's just too much vibration in this instrument. Now, Edward Morley, a man who understood significant figures, was a great help in helping him to create the next instrument. So there we see German craftsmanship, fine design, curvy lines. I bet those knobs on the screws that move the mirrors were like works of art. Well, here's American craftsmanship. It's a slab of rock floating in a pool of mercury. It's huge. It's tough. It's like the Mustang to the Lamborghini, right? I mean, it's big, it's powerful, it's got a giant engine. This was very stable. That giant rock was not going to vibrate. You'll see that they had lots of mirrors there so that they could multiply the path length. You can read all about that if you want to read about the experiment itself. This is an interferometer. Now, what is an interferometer really? Let's take a look. All right, so let's discuss an interferometer and its effect on light power hitting the detector. Let's zoom in on the important part here. Here's a highly simplified diagram of an interferometer. Imagine that you have a light source. So we have a light source here. And this light source, obviously in an IR, is designed to emit light that includes the IR frequencies that we're interested in. And that light is going to encounter this beam splitter here. So the light is going to leave the meter or the source, and it's going to hit this beam splitter. And a beam splitter is just a partially silvered mirror. This would obviously be a mirror made of a material that reflects IR light, and the transparent part of the material is a material that lets IR light through. Now we can reflect off that mirror, and obviously we'll reflect in this direction, or we could pass through, since it's partially reflective, toward that mirror. So the light passes through, and then it bounces off of those two mirrors. Those are real mirrors, so the light just bounces off of those and comes back to the beam splitter. At the beam splitter, you have a choice. The light coming from this direction can pass straight through to the detector or head back toward the light source. The light coming from this direction can pass straight through the light source or be reflected toward the photodetector. So at this point, we lose half our light, but that's okay. Light's cheap. You just turn it on, right? It's just electricity. So we're getting half the light from the light source reaching the photodetector. And there it goes. Now, if both of these path lengths are exactly the same, then the light doesn't change. I mean, basically, if this light beam travels through 10 feet and it also travels through 10 feet in another direction, and you bring it back together, it's going to be the same light beam. So if the two path lengths in this direction and this direction are exactly the same, no change. But what if that's not true? What if I move a mirror? And here we see a moving mirror. Now, at this moment, we are at a condition called zero path difference, where we have actually arranged for the two mirrors to be exactly the same distance apart. So the two paths that the light travels is exactly the same. And we're going to be getting a certain power detected by the photodetector. And I'm going to plot that. I'm going to plot it right here. There it is. Power against the distance that we've moved the mirror. Because I'm going to move the mirror. I'm going to do an experiment. What happens if I move the mirror? All right. So the power depends on the phase of the light when it hits that photodetector. If the two segments of light that were separated and recombined are in exactly the same phase, basically meaning they're exactly in their original state, we'll have maximum power. If they're not lining up perfectly, we'll have not a complete addition of their power, and therefore we'll have less power. So let's see what happens here. Let's move the light a little bit, or the mirror a little bit. Look what happened. I moved the mirror. Look at the difference here. I moved it that little bit. It resulted in, now at this point, the light is completely out of phase. It's canceling itself out at every single step as it passes through or as it reaches the photodetector. And look what happened here. We're now at a minimum of power. If I move the mirror another little bit, and I change the path length by, in total, a complete wavelength now, I have gone through a minimum at half a wavelength of distance change and back to the maximum at a full wavelength of distance change. So I can turn a light signal into a power signal, and that power signal has the same wavelength as the light. So if this was a laser beam shining through, I would actually see it oscillate. Here I've moved the mirror just a little bit, and I see the power reducing. I move it a complete half wavelength. I'm at a minimum. Let's go crazy. Let's just start moving that mirror, and you can see that the power oscillates with a wavelength that is equal to the wavelength of light. So if I know the distance I've moved that mirror, and that's its own engineering challenge, but it has been solved, and it can be done rather cost effectively, and that's why an FTIR sits on your bench and not in a locked room inside a vault with a person wearing a white coat operating it. I hope you're wearing your white coat when you're in the lab. Now, this is what a FTIR experiment would be. We start the mirror at one location because we don't really know where zero path difference is. I mean, come on. To actually fix two mirrors exactly, 1 billion wavelengths apart from each other, and exactly there, not one being 1 billion and one being 1 billion and one, both being 1 billion wavelengths apart from each other. That's like, how can that happen? So you just start the mirror in one place. You move it through the zero path difference and then off to the other side. So let's just do that. We'll just start the mirror moving. At some point we hit zero path difference. We don't know where that is, although we will see it as a maximum signal in our interferogram. So we'll know where it is when we see that signal. And then, you just keep it going. And there's your interferogram. That's what you get if you did an interferogram of laser light. Just an oscillating power signal. Now, if I just shone that laser on the photodetector, all I would get is just, hey, lots of power. We just get one single number, it would stay the same. Lots of power till I turn it off. But using the interferometer, I can turn that power signal into an oscillating power signal with the same wavelength of light. Now that I know the wavelength of the laser beam, if I knew the frequency of that laser, I would be able to calculate the speed of light. If I knew the speed of light, I would be able to calculate the frequency. So other work by other scientists had determined the frequency of a particular band of light, and from using the interferometer, Michelson was able to determine a very precise number for the speed of light, and that's really what he won the Nobel Prize for, determining the exact speed of light. And of course, if you know the speed of light, then suddenly astronomy can be used to very precisely measure distances to objects. I mean, really, people who come up with very precise measurements really help the world do things. If you want to know how far the moon is away, to the nearest centimeter, to the nearest millimeter, you need to determine exactly what a meter is. And let me tell you, that stick in Paris is not precise enough. You need to use basically a measurement based on laser light to determine what the meter is, and that's what it's been redefined as. All right, so there's our interferometer. Let's reset things, and let's talk about this sort of on a step-by-step basis here. So here's a whole bunch of series of sort of situations where we move the mirror a little bit, and I want to talk to you about how we get that power signal. So let's zoom in on the first one. So here we have the two wavelengths have come out of the interferometer, and there they are. They're exactly the same phase. I'm just going to show you that the phase alters, or the power alters according to wavelength, and everything is timed perfectly. I'm just going to put them together there, and I want to call your attention to this little tick here. Right now we're at zero path difference. Well, if I add up these two beams, what do I get? I get a particular power signal. Well, let's measure that. How am I going to measure it? That's what the photodetector does. Imagine that the photodetector is kind of like, I don't know, a caliper that measures the power that's in that wave. All right, so here is the power that's in that wave. Let's plot it on the plot here. There it is. So we have a set power for a set distance. Let's move that distance a little bit. What if that distance changed by a tiny amount? What if, say, we change the distance between the two beams by, I don't know, just a tiny bit, an eighth of a wavelength? How about that? What happens there? Well, add them up. When we add them up, we see it's not as much power in that beam anymore. There's a slight amount of canceling because they're not lined up. Well, let's measure it. Let's take our caliper here and measure that. And what do we get? Look at that. Less power. All right, so let's take our wavelength here and let's move it a tiny bit more. All right, now we're a quarter wavelength in the difference. Well, there's what we add up to. Notice less power. Let's measure. Notice less power. Let's keep doing that, all right? So we're going to move our wavelength, or move our mirror just another bit. 3/8 of a wavelength will be the difference in path length now. And add things up. What do we get? Less power. All right, well, what does that come to in our graph here? Let's measure it. Ooh, look, a lot less power. All right, well, how about we move the mirrors just a tiny bit more? Okay, we're getting ready to move the mirror. Okay, watch as we move the mirror here. I'm gonna move the mirror a little bit. There we go. Now I've moved it a half wavelength. When we move the mirrors a half wavelength, what kind of power signal do we get? What kind of measurement are we gonna add up to here at the detector? Well, let's see, we get nothing. That's the signal that's reaching the detector. It's completely canceled out. So if I measure it, what do I get? What if you measure? You get 0, right? So we're going to measure it and we're going to see what we get here. Oh, we get 0. Now I'm going to move it a little bit more. Let's speed things up. Let's move it a third of a wavelength from where we are, okay? So I'm going to move it a third of a wavelength. We're getting ready. Here we go. Chunk, a third of a wavelength. So now we're 2/3 of a wavelength from where we started. And what kind of power do we have? Well, it looks like we've got some power in the signal now. Let's measure it. All right, so we're going to measure it. There's our value, and so let's put it on the plot over here. What do we get? Oh, look, we're coming back up in power. And so let's move it another third of a wavelength. All right, so we're going to get ready to move it a third of a wavelength here. There we go. What does that add up to? Oh, even more power. Let's measure that. Let's put it on the plot. There we go. Now let's move it another third of a wavelength, which would give us 6/6 of a wavelength. You know what that is? That's a whole wavelength, right? So we're going to get ready to move it. There we go. Add it up. We get basically the original power, right? We're back to things being lined up, even though we moved a whole wavelength. Look, there is one beam. That's how much out of phase it is. It's out of phase a whole wavelength before it finally starts lining up with the other beam, because it moved a whole wavelength further. It's a whole wavelength behind. And that's what the interferometer does. Look, we're a whole wavelength behind. The mirror moved, and it changed the path length by a distance equal to a whole wavelength. Remember, since the mirror goes two ways, or the beam goes two ways when it reflects off the mirror, we're going to have a situation where we only have to move the mirror half the distance to create that whole unit of distance change in the wavelength. So by moving the mirror half a wavelength, I've created a whole wavelength distance change in my beam. What does that come out to when we go to the graph? Back up to maximum power. And if we just kept moving this, we're going to see that we're going to get an oscillating signal, an oscillating power signal equal to the wavelength of the original. So look over here, we're moving the beam, and what do we get? We got an oscillating signal, a power signal equal to the wavelength of that laser light. So I can turn any light signal into a power signal, and a power signal is something that a computer can read, and that's the important element that an interferometer does. By causing the light to interfere with itself because of the changing path length of the mirror, we can create a system where we can measure every single wavelength that's in that light using electronics. And that's the key. Everything that happens to the spectrometer has to be, manipulated by electricity. It's not just you looking at it and going, it's blue! No, it has to be manipulated by electricity, and a dumb computer, which does not have a clue what blue is, will give you a number for the wavelength. And I guess this is redder than red because we're in infrared, aren't we? So there's all the possible sort of conditions, and I invite you to go through this and look at it in detail, model it. I did all of these calculations in a mathematical package. There's lots of ones available: Maple, Mathematica, MATLAB. There's even free ones such as Maxima, which you can download off the web. Runs on most systems, absolutely free, does the same thing. So if you can figure out how to do this with a math package, I have some notes on how to do it in Maple in the document that accompanies this lecture. Have some fun. Add up some waves. Add up their power. See what it comes to. See if you agree with this graph. And if you don't agree, come see me or talk about it on the class forum, and I'll tell you why this graph is right. All right. So that's sort of the notes on the Michelson interferometer. Now, what if there's more than one frequency? Well, that's a different system, isn't it? So let's take this case here, where we're starting off with a signal that has one wavelength, and we compare it to a signal that has two wavelengths, and we compare it to the combination of those. So here I have combined these two signals, a signal with a wavelength of 1 unit and a signal with a wavelength of 1/3 of that. Or what you could say is this has a frequency of 1 wave number per unit of distance, and this has a frequency of 3 wave numbers per unit of distance. And I'm going to use wave numbers. Now, frequencies in IR are generally discussed as being between 500 wave numbers and 4,000 wave numbers. So basically, the wave oscillates 500 times in a centimeter or up to 4,000 times in a centimeter in the range that we look at with most of our mid-IR spectrophotometers like the one on your bench. Why that range? Why not more? Why not less? Well, it contains most of the information we're interested in. Also below 500, we kind of run out of materials that will let IR to pass through them easily. So instruments that look below 500 are much more expensive and use different techniques to measure the IR radiation. Above 4,000, not a lot of really useful information. And again, we'd have to actually change the source because our IR source isn't producing wavelengths much above that. So you got to go to a different instrument there. But there's the near IR, the far IR. Those are all important regions of the spectrum to look at when you're looking at molecules, especially if you're an astronomer and that's all you've got. But in our lab, our instrument looks at the mid IR, which is 500 to 4,000 wave numbers. And so here I'm looking at 1 wave number and 3 wave numbers. So these are imaginary. There's no frequency like that. That's like less than sound, isn't it? But we are looking at a system here where we're sort of imagining 1 wave number and 3 wave number. And look how they combine. Look how they combine here if I actually combine those two signals. Does that look like a signal that you could easily, just by looking at it, determine the frequency? All we get from the interferometer is a power signal. The power signal has the particular wavelength, but if we're adding together signals of different wavelengths, you get this sort of different signal. That doesn't look like a sine wave, but it actually contains both. What if we added up a whole bunch of frequencies and they were close together? Because remember, I mean, really, the light is producing basically every frequency. It's not just producing between 500 and 4,000, it's producing lots of frequencies beyond that too, and every frequency between those frequencies. I'm modeling it in a clumsy way by just adding together 6 frequencies from 1 to 6 wave numbers here. So what happens when I add them together? Well, so here we got a frequency with 1 wave number here, that one that comes down and comes back up. And then there's 2 wave numbers. You might barely be able to see that. Up, down, up, down. The rest kind of become complicated to see. But one thing we notice is at the very beginning, they're all lined up. All right? And after half a period, look, 3 up, 3 down. They're kind of canceling each other out. And really, there's no point along here where they're all lined up again, is it? I mean, they're kind of in between lined up to the worst case here at the end. They add up to something that looks like this combined signal. Starts strong, settles down. Basically, there's a center peak and then what we call a wing that just goes out. And if you're looking at IR, which of course would have an infinite number of frequencies between every single one of these frequencies, it settles down pretty quick and stays pretty quiet in the wing. So you need an instrument with low noise to measure. This is the important signal out here. Look, you need at least a couple of oscillations to get the frequencies. So you need to measure this sort of tail as it goes out, as you move the mirror, as the optical path difference changes. And the sum of those frequencies starts strong, gets weak real fast, stays weak. We're measuring. This is the key part here to measure. The more of that we can measure, the more information we're going to get out of the spectrum. So we can combine those frequencies, and when we combine them, at 0 path difference, we have maximum strength, but they just get more and more out of phase as they travel along. Now, look at this signal here. Do you think you could just stare at that and tell me the frequencies that are involved? Well, I can tell you that there's at least one frequency of 6 wave numbers because just by the math I did, the fine vibration would be the highest wave number signal. But I really couldn't tell you much else about it. How are we going to solve this problem? Well, that was 5. Let's do 30. Now, you might say, but Barry, how are we going to do 30? Well, you just use Maple or any math package. Just add them up and plot it. I just plotted this function here. So I did, basically that I is 1 to 30. So basically 1 to 30 oscillations per period of distance, which I'm imagining being a centimeter. And there we go. Look, the big center peak. And that value right there, that represents the original amount of infrared radiation that your spectrometer can receive. That's it. That's how much IR it's receiving. If that is low, your spectrometer is going to know not much light is getting through your sample. It might even say, hey, buddy, make a better sample. I can't see anything. Or it might say, hey, buddy, my lamp is burned out. Get another one. Write a check. So that you can measure actually how much energy is getting through your sample by really just the original peak. And then look how quickly it settles down. This region here is where the information is. I mean, all of it has the information, but this is going to just go on forever. As long as your instrument doesn't have too great of a noise, you'll be able to see that signal for a good long time, and you'll be able to measure it. What if I take one of the frequencies out? Look here, I just subtracted the 10 wave number signal. So really, I'm looking at all 30 signals except for the one that has 10 wave numbers. Look at the change in the signal. I mean, really, we went from something that had a regular pattern to something that doesn't. Look, there's information there. I can tell something's up, right? So there's your sort of initial condition where you have all the frequencies, and now I know something's up. Well, what's up? We lost a frequency there. Maybe our sample absorbed 100% of the 10 wave number frequency. Well, what can we do with that? Well, we have to figure out how to determine what frequency is missing. Over here, I subtracted 2 frequencies, and again, you can see it's different than the original. Again, something's up. We lost another one. So that information is in there. The computer, using Fourier transform, which is the subject of another presentation, can determine exactly what frequencies are present in this signal. So let's do a big interferogram. All right, let's do this puppy here. There's sort of a simulated interferogram that you would get with your IR. All right, let's start off with this idea that we can have a interferogram that represents sort of every single wavelength that's coming through your sample. Now, your instrument interferogram is not going to look like this because this is faked using Maple. Your instrument, of course, does not have the same power of light being emitted at 4,000 wave numbers as at 500. It maxes out really in power around 1,200 wave numbers and then tails off toward either end. So, I mean, you have it's not going to look like this, but this is sort of a cartoon or an imaginary perfect world representation of every frequency in unit frequencies between 1 and 3,500 wave numbers. Now, of course, I'm not looking at all the frequencies between those frequencies because, that's an infinite number and I will only live so long. My computer is slow. So as we move the mirror, I'm going to move the mirror from whatever point this is to whatever point this is. Really, in the math here, I'm moving it from 10 millimeters out from zero path difference to 10 millimeters past zero path difference. And as I move that mirror, of course, all the frequencies are out of phase here. There comes a point where suddenly there's that one magic point where they're all in phase. And that's the maximum power. And then, of course, we have another wing out here. Well, that is every frequency that's there. If I zoom in, I see this regular pattern. And of course, that's only there because we're looking at unit frequencies. If you look at every frequency in the universe, that's just going to be more of a straight line. So let's consider if I take out some frequencies. Imagine I put a sample in. And in that sample, I am absorbing in the region of 1800 to 1830 wave numbers, and absorbing in the region of 2850 to 2950 wave numbers. Those two sections have been removed. What do we see? Look at the information in the interferogram. I can see that something's up. There's the function I typed into Maple to do this. Something is up. I can use a technique called the Fourier transform, which will tell me every single frequency that's in that wave. It will give me a list. I can basically use the Fourier transform to ask, is this frequency present? And if it is, it'll give me a number, which is proportional to the intensity of that signal in its contribution to this whole pattern here. And so if that particular wavelength is there, I get a number. If that particular wavelength is not there, I get 0. So there it is sort of blown up. I can see this information here. Compare it to this. There's information there. All right, well, let's analyze this. Well, we can go to the Fourier transform. And what are we going to get? Well, Joseph Fourier was a very important mathematician. The Fourier transform is an incredibly important piece of math, and I guarantee you right now you can't live without it. Every single thing you do on your smartphone is based on the Fourier transform. And I'll leave that to physics to explain to you. But here is the Fourier transform of this signal. Remember, I just faked this signal. I mathematically made it up. It shows me all the frequencies that are present. It gave me a value, and I had them all equal with equal intensity. So basically, I get the same value for every single frequency, except the ones that I cut out. And I get a value for every frequency, except the ones that I cut out. And so doesn't that look like the IR spectra that I've showed you already? You know, pretty much you have what doesn't absorb and what does absorb as negative peaks. So that's what the Fourier transform is going to do, and I hope that you will pay some attention to the Fourier transform presentation and get a sense of its power, and of course its limitations and some technical details about it that you have to think about when you're using your instrument. And of course it's going to become really important when we talk about NMR, because NMR signal processing uses a lot of details and things that you can change with the math of the Fourier transform. In IR, things are pretty cut and dried. I mean, basically, press go, the startup conditions of your instrument are going to be fine. In NMR, there's going to be times all your life in chemistry where you're going to be wanting to mess with the settings in your NMR to find a particular frequency, to zoom in on certain areas, to eliminate water peaks. There's all kinds of tricks you can pull with the electronics of an NMR, and the Fourier transform is going to be part of that. So there's sort of the notes on adding up frequencies in the interferometer. So the interferometer is an absolutely sort of essential and very clever engineering marvel that is in your instrument, and there's another presentation on sort of the physical aspects of your instrument, where the light source is, basically how your interferometer is built. There's lots of ways to build them. Just Google interferometer. There's tons of high-tech companies out there making interferometers for spacecraft, for spy satellites, for scientific experiments. There's an interferometer in Oregon that has arms that are 2 kilometers long, and they're trying to measure subtle changes in the distance of space-time, as if space-time would sort of randomly contract and expand to detect gravity waves. I haven't seen any gravity waves yet, but they're working on it. I hope you enjoyed this presentation. We'll see you in class.